In mathematics, the packing dimension is one of a number of concepts that can be used to define the dimension of a subset of a metric space. Packing dimension is in some sense dual to Hausdorff dimension, since packing dimension is constructed by packing small open balls inside the given subset, whereas Hausdorff dimension is constructed by covering the given subset by such small open balls. The packing dimension was introduced by C. Tricot Jr. in 1982. Definitions. Let be a metric space with a subset Sx and let S0. The S-dimensional packing pre-measure of S is defined to be, unfortunately, this is just a pre-measure and not a true measure on subsets of X, as can be seen by considering dense, countable subsets. However, the pre-measure leads to a bona fide measure. The S-dimensional packing measure of S is defined to be, i.e., the packing measure of S is the infimum of the packing pre-measures of countable covers of S. Having done this, the packing dimension dimp of S is defined analogously to the Hausdorff dimension. An example. The following example is the simplest situation where Hausdorff and packing dimensions may differ. Fix a sequence such that an define inductively a nested sequence of compact subsets of the real line as follows. Let, for each connected component of delete the middle interval of length, obtaining two intervals of length, which will be taken as connected components if. Next, define. Then is topologically a Cantor set. For example, will be the usual middle thirds Cantor set if it is possible to show that the Hausdorff and the packing dimensions of the set are given respectively by. It follows easily that given numbers, one can choose a sequence as above such that the associated Cantor set has Hausdorff dimension and packing dimension. Generalizations. One can consider dimension functions more general than diameter to the s. For any function h, 0 plus infinity, 0 plus infinity, let the packing pre-measure of S with dimension function h be given by and define the packing measure of S with dimension function h by the function. H is said to be an exact dimension function for S if pH is both finite and strictly positive. Properties. If S is a subset of n-dimensional Euclidean space Rn with its usual metric, then the packing dimension of S is equal to the upper modified box dimension of S. This result is interesting because it shows how a dimension derived from a measure agrees with one derived without using a measure. Note, however, that the packing dimension is not equal to the box dimension. For example, the set of rationals Q has box dimension 1 and packing dimension 0.